You know, we've been promised robot butlers for what, decades now, but the reality is they're still not here. So today, we're going to dig into why and how a totally new way of teaching robots to think is finally about to change everything.
I mean, it's the classic sci-fi promise, isn't it? A robot that can just tidy up your room, do the dishes, maybe even fold your laundry. But if you actually look around your home, that promise feels, well, pretty far off. So what's the holdup? What's taking so long?
Well, the reality is that most robots leave here, in factories. They're absolute masters of repetition, doing the same exact thing over and over in a perfectly controlled environment. But our homes? They're chaotic, messy, unpredictable, and that's a world where these traditional robots just completely fall apart. And it all comes down to how they were first designed to think.
Okay, so let's start with the classical approach. And the best way to think about these robots is as hyper-intelligent calculators. Seriously, they don't learn, they compute. Every single little move is the result of a precise, pre-programmed mathematical equation.
You know, this ancient piece of wisdom, it actually perfectly sums up the whole philosophy of classical robotics. For a robot to do anything, it must have a perfect mathematical model, a literal blueprint of itself and its entire world. Everything has to be known, down to the millimeter, in advance.
The key thing to get here is that these robots don't learn from experience at all. Human engineers spend ages building a perfect digital model of the world, and the robot just uses really complex math to operate inside of it. It uses things like inverse kinematics, which is just a fancy term for the math it needs to figure out the exact angle for every single joint in its arm to place its hand at one specific point in space.
And this all follows this really rigid three-step pipeline. First, the robot's camera senses a screw. Then, its processor plans the one single perfect path to it based on that internal blueprint. And finally, its arm acts, executing that path with perfect precision. It's incredibly precise, yeah, but it's also incredibly fragile.
And here is where it all just breaks down. If a coffee cup is just a half an inch from where that perfect blueprint expects it to be, the entire system can just fail. This approach is brittle. It takes a massive amount of engineering for every single new task, and maybe worst of all, it can't learn from the mountains of real-world data we have now. This is exactly why these calculator robots are stuck in factories.
So if pre-programming everything is a dead end for the real world, what's next? Well, why not have the robot learn on its own? And this brings us to reinforcement learning. The absolute best analogy for this is a toddler. A toddler doesn't have a blueprint for the world. It learns by poking things, trying stuff, and just seeing what happens.
The core idea here is actually pretty simple. The robot, which we call the agent, tries some action. If that action gets it closer to its goal, like picking up a block, it gets a little digital reward. If it does something wrong, like dropping the block, it gets a penalty. Over and over again, it tries to learn a strategy or a policy to get the most rewards possible.
So this kicks off this constant learning loop. The robot observes the world, it acts, it gets some feedback, and it updates its internal strategy. And it repeats this cycle millions, sometimes even billions of times, slowly getting better through pure brute force trial and error.
But, as you can imagine, this toddler approach has huge problems for physical robots. I mean, we don't let toddlers operate heavy machinery for a reason, right? Early attempts can be dangerous, breaking the robot or things around it. It's also ridiculously slow. You can't have a real robot try and fail to pick up a glass 1,000,000 times. So most of this has to happen in a perfect computer simulation, which creates something called the reality gap. What works in the perfect simulation just doesn't work in the messy real world.
Okay, so this leads us to a much more practical and, honestly, a much more powerful idea. If learning from scratch like a toddler is too slow and dangerous, why not have the robot learn like an apprentice by just watching an expert?
So yeah, instead of all that blind stumbling around in the dark, we're going to give the robot a much better starting point. We're going to let it learn from a pro.
And that solution is called behavioral cloning. It's pretty cool. You get a human to do a task, either by physically moving the robot's arm or using a remote control, and you just record everything, every camera image, every motor command. Then the robot's job is simple. Just imitate what the expert did.
This quote from the father of cybernetics, Norbert Wiener, just nails it. Instead of trying to write down a perfect mathematical model of how to pick up a cat, just show the system a cat. The successful demonstration is the model. It's a brilliant way of looking at it. But, of course, there's a but. This introduces a brand new and really tricky problem. It's called multimodality. Just think about picking up a pen from a table. You could grab it from the left, from the right, maybe from the top. All of them are perfectly correct. So how does a robot learn when its training data shows multiple, totally valid solutions for the exact same problem?
And this is where simple imitation just completely falls on its face. If the robot sees 50 examples of grabbing an object from the left side and 50 examples of grabbing it from the right side, a basic learning algorithm might literally average them together and try to grab the empty space right in the middle, failing every time. It turns out, averaging two awesome solutions can give you a truly awful result.
And solving this very challenge, this multimodality problem, is what's pushing robotics into its most exciting phase yet. It's connecting it directly to the massive AI revolution we're seeing all around us with things like large language models. This is where we get to the future, the generalist robot.
So real quick, let's recap our journey. We started with the rigid calculator robot with its perfect blueprint. Then we moved to the clumsy trial-and-error toddler, and finally to the apprentice that just imitates an expert. Each one got us closer, but each had a pretty big flaw for real-world use.
You see, the fundamental goal itself is changing right under our feet. We're moving away from building these hyper-specialized robots that can only do one single thing perfectly.
And we're moving toward creating a generalist, a single robot running a single AI model that has a foundational understanding of how the world works so it can learn a huge variety of tasks, just like you and I do.
So how do we actually do this? Well, we take that Apprentice idea and we put it on steroids. Researchers are training these enormous AI models, the same type of AI that powers stuff like ChatGPT, on gigantic, diverse data sets of human demonstrations. These foundation models for robotics aren't just memorizing one task. They're starting to learn the underlying physics and logic of how to interact with our world. In a very real way, they are finally learning to think.
So as we get closer and closer to this actually being a reality, the final question isn't just a technical one anymore. It's a personal one. When this technology finally arrives and you have a generalist robot in your home, what's the very first tedious, boring, or difficult task you're going to make it do? Let me know.